Hello, everyone. I'm going to be going over mod 4. This is section 28, extensions to linear regression. I'm going to be going over interaction terms, polynomial regression, bias variance trade-off, and then ridge and lasso regression. So covering a bunch of topics. Going to be doing something new and just see how it works out. I'm going to be doing, they have an option of turning Jupyter notebooks into slides. You can make it a slideshow. So I'm going to be trying that today and seeing how that works. So this is extensions to linear models, interaction terms, and polynomial regression. So to start, this is a Jupyter notebook. So with a Jupyter notebook, import statements, I'm importing using pandas for this lecture. I'm going to be using NumPy, Seaborn, Matplotlib, linear regression, which all this so far you should be familiar with. Lasso and ridge regression, these are two new types of regression that I'm going to be talking about. Also going to be using polynomial features and the standard scalar and train test split we're familiar with, and mean squared error for calculating the error. So this is the equation for a linear regression. You have B naught, which is the y-intercept, and then beta 1, beta 2, all the way up to beta n. So these are all the slopes for all of the coefficients. So one of the problems is, by construction, this model assumes that there's a linear relationship between the target variables and the features. But what about times when features have a non-linear relationship to the data, or when features interact with each other? So that's where these interaction terms and polynomial regression kind of comes into play. So what an interaction term, it allows you to model the relationship that two features have an interaction with each other. So if we have two features and we think that if they have an interaction with each other that has an impact on the target variable, then we can a lot of times you'll multiply them together. So we have x1 times x2. So on the housing data project from the King County data, if we thought square foot living and number of floors, I can't remember if there's a number of floors in that data set or not, but you could do like square foot living divided by floors because you think the square foot living on the average square foot living on each floor might have an impact. So that's just one example. That's just one I thought off the top of my head. And then another option is this polynomial regression. Polynomial terms allow us to capture nonlinear relationships between a feature and the target. So if we think that a feature has a relationship with the target, but it's not a straight line relationship, you can square it or cube it. And so if square foot living, if you don't think square foot living has a linear relationship with the price of a house, maybe it has an exponential relationship where price really skyrockets after a certain point, you could square foot living and then put that in your regression. And there's a module for this. Scikit learns polynomial features. I'm going to be covering that a little bit later, just going over some like kind of broad terminology right now. And this is a super important part of machine learning. As you start doing, if you take a look at Kaggle competitions, you'll find that when people are, with the data set is tabular, so it's not an image data set or not a text data set, people will pretty much use the exact same algorithm, gradient boosting, and which is a algorithm that we will teach later on in this course. But the difference between the person that gets first place and the person that gets 10,000 or 1,000th place because there's a lot of people that do these competitions, is feature engineering. It's being able to create new features. So definitely keep that in mind. Spend some time in the feature engineering and to really get a good understanding of like which features to create, because you don't because you can kind of do this blindly, but it's going to be more efficient if you can kind of understand like, okay, I should probably square this feature, I think, or these two features look like they should interact. It's by doing EDA, but it's by getting a really good understanding of the data. So now let's discuss one of the most important concepts regarding model fitting, the bias variance trade-off. Bias variance trade-off. And this is not all showing up. So when fitting a model to data, there are two main sources of error, reducible and irreducible error. Reducible error is comprised of bias and variance. So bias is error. Bias error is an error from incorrect assumptions in the model. When a model has too high bias, it can miss relevant relationships between features and target, and can cause a model to underfit and not be able to generalize to unseen data. So let me read the definition of variance, then there's a visualization at the bottom that I think is pretty useful that I want to show. Variance is error due to sensitivity to variations in the training set. A model with too high variance trains on the noise rather than the signal, and also doesn't generalize to unseen data and overfits it. Yeah, so this image right here, and there's supposed to be an image in here. Here it is. Let me bring it up a little bit. So bias, and let me go back to the definition. Bias, error from incorrect assumptions of the data. When a model has too high bias, it can miss relevant relationships between features and target and cause a model to underfit. So when you have high bias in a model, that means your model never really understood the underlying relationship between your predictors and your target. So it's underfitting. And then going to the variance, model with too high variance trains on the noise rather than the signal and doesn't generalize to unseen data and overfits it. So when you have high variance, that's your model has essentially like memorized the training data and is not going to do well to data that it's never seen before. So it's overfitting. So bias error measures how much the predicted values of your model differ from the true values. Variance error occurs when a model is very sensitive to specific sets of training data. If your model has too few predictors, or if it has too much data in your training set, it might suffer from high bias and underfit your data. So if you have too few data in your training set, or too few predictors, it's never going to learn the underlying relationship. But on the other side, if your model is too complex and has too many predictors, it might suffer from high variance. In either case, it's not going to do well in generalized to unseen data. The idea here is that you want to train models with just the enough number of features to minimize the model's generalization error. And then we can use some technique called regularization, which we're going to discuss next. Then I have one more diagram that I want to show. This is from Wikipedia. So this is a classification model. So you're trying to predict whether it's a red or get a decision brown boundary for red versus blues. So the green line, it gets a 100% accuracy. However, it's way overfitting, and this model is not going to generalize to unseen data. It does perfect on this data, but it looks like overall that these blue points are probably outliers, and we don't want to predict them, and these red points are outliers. So this black line right here is more of a generalized model that's going to, or they say a regularized model that generalizes, going to generalize to unseen data a lot better. So regularization now. Now suppose I have split my data into training and testing sets. Do I want my model to fit my training data exactly? No, you do not. A model like this will have too much variance and overfit the data. It won't generalize to the unseen test data. So looking at this question again, do I want my model to fit the training data exactly? If I get a perfect score of my training data, I'm usually going to be really concerned. If I get 100% accuracy or a 0 mean squared error, something's fishy is going on there. I'm going to assume that my test accuracy is not going to be 100%. My test mean squared error, if it's a regression problem, is not going to be 0. So, yep, overfitting generally a result of high variance. High variance can be caused by having irrelevant or too many predictors. So if we're predicting the price of houses and we have the average weight of squirrels on that day that the house was sold, like that's probably pretty irrelevant. And having a feature like that is just going to confuse your model, especially if it has a high coefficient for that. So the high coefficient, it's going to be it's going to have a lot of weight in your model. So multicollinearity, so features that are highly correlated with each other, so square foot living and number of bedrooms, and then large coefficients. So large coefficients in a regression model, they have bigger impact on their model. So if you have a feature that has a really high coefficient, that feature is weighted really high in your model. And that may be representative in the training data, but it doesn't always generalize very well. So the first problem is about picking up on the noise rather than the signal. That's having too many predictors. The second problem is about having a least squares estimate that is highly sensitive to random error. That's correct. And the third is about having highly sensitive predictors. So what can we do for that? We can use something called regularization. Regularization is about introducing a factor into our model's cost function designed to enforce the structure that the coefficients stay small by penalizing coefficients that get too large. This technique helps us avoid overfitting as it discourages learning a very complex model. So it's going to be shrinking all the coefficients down. To implement regularization, we alter the linear regression cost function such that the goal now is to not merely to minimize the difference between the actual values in our model's predicted values. Rather, we add a term to our loss function that represents the sizes of the coefficients. So let's go back to this bias variance trade-off and talk about this. So it's really easy to have, if you have high variance, you're prone to overfitting. Your model's not going to generalize well. So what regularization does is it's going to add a little bit of extra bias to your model so that your training results are not going to be as good, but with the idea being that your testing results will be good. So it adds a little bias to it, but by adding a little extra bias, it's going to increase your variance. It's going to decrease your variance, which is what you're looking for. So there's two techniques that we're going to be going over. Lasso, this is also called L1 regularization, and then we have Ridge, which is also known as L2 regularization. So these formulas are pretty nasty. So this formula right here, this is your y actual minus the predicted value. So it's just your regular cost function, and this is being cut off. So let me go to it. And the only difference between the two is Lasso regression takes the absolute value of each of the coefficients, and then ridge regression squares each of the coefficients. This lambda, I'm always bad with Greek symbols. I believe that's a lambda. This lambda is a penalty term that we multiply each coefficient by. So, and this can be it has to be a positive integer. So it can be 0 to infinity. And you'll typically will want to tune that. So if lambda is 0, this part is going to be regular 0. This part is going to be 0, so this is just going to be regular least squares regression. But then as you start adding to it, the larger the value, the bigger the penalty is going to be for large coefficients. And yeah, so lasso regression again uses the absolute value. When you increase the lambda, the coefficients will actually go to 0. So you can use lasso regression for feature selection. So features that are not useful in that regression model will have a coefficient of 0. So they're essentially you're essentially getting rid of them. Then ridge uses the squares of the coefficient. As the lambda increases, your coefficients will approach 0, but will not actually equal 0. So lasso regression, I'll typically use if I have a ton of features and I'm not sure what are the best ones to use. Ridge regression is good to use if you're pretty confident you have the right number of features. So it's typical, sometimes people will actually use lasso regression to select the important features, then put it into a ridge regression model. So yeah. So yeah, we want to scale the features before regularization. We need all the features to be on the exact same scale, or the features will be weighted unequally. Yeah, think of it as when you use recursive feature elimination, you're going to want to you have to scale the features so that everyone's on the same weighted the same. So same way with regularization. And now we're going to go into an example. And I'm going to be going back to my notebook. I want to run this cell right here. And so what I'm doing right here is I am loading the Boston housing data set. The Boston housing data set is a data set that is stored on scikit-learn. Pretty famous data set, bunch of information about houses in the Boston area. Very similar to King County, but Boston data, and I believe it's a lot older. So what I'm doing here is first making it a data frame, and then separating my data into X and Y, doing a train test split, 70% train, 30% test. I make an instance of my linear regression model. I fit my data. I want to take a look at my training score. And then I want to take a look at my testing score. And then I'm going to calculate my mean squared error on my training data and my mean squared error on my testing data. So training score in regression on scikit-learn, this is what my R squared is. So I get a R squared of 0.74 for my training, a R squared of 0.71 for my testing. And then my training mean squared error is a 22, and my testing mean squared error is a 21. So let's first attempt to improve upon the model by adding polynomial features and interaction terms. We created the polynomial and interaction terms that fit the model for you. So let me run this. So this X-train poly, let me look up let's look up what the documentation for scikit-learn polynomial features. That was it, right? Oh yeah, I was wondering what so yeah, it's gonna square all of my features. So degree equals 2. So yeah. So it is squaring all of my features. So I go in from, I have 104 features now. What did I originally have? X train shape. So I went from having 13 features to 104 features. So ton of features now. At this stage, so my train mean squared error is 4.6. It previously was 22. So it pretty significantly decreased my training mean squared error. But at this point, I'm probably pretty high bias or high variance right now. So we're going to do the same thing with the test. And it doesn't like that it has none, so I need to update that. So X test. And then I want to do X test poly. I want to, and Y test. And then I want to predict with X test poly. And on the test data, so this should be Y test. And yeah, so here's definitely a big sign of high variance that I'm overfitting. So the mean squared error on my test data set is 25. It was 4.6 for my training data set. And the R squared is 0.66 versus 0.95. So definitely overfitting on here. So now we're going to use lasso regression. Again, lasso regression is good for when you have a bunch of features and you think some of them may be irrelevant. We remember we have 104 features. We probably think some of these are irrelevant. So we're going to scale the features first. And get a drink of water. So we're going to set the alpha level to be 0.3. The alpha level is, it's kind of confusing. This is whatever lambda is in this equation. They use a different Greek letter for it. So just know it's 0.3. We're going to set the random state to be 1. And then we want to train our model. So we went X train scaled poly and Y train. All right. So now we want to compute and print the R squared of the model in the training data. So we want X train scaled poly. No. Train scaled poly and Y train. Compute and print the mean squared error. And I want to do my prediction on X train scaled poly. And yeah, let's run that. So I get a mean squared error. So I got a R squared of 0.85 and then a training mean squared error of 12. Where did that go? There, right here. So it was 0.95, now it's like 0.75, and I get a training mean squared error of 4, and this time I got a 12. So I added a little bit of bias to my model, so hopefully at this point I've right around here where I'm not so high variance, or I guess technically you want to be right here, where you have a little bit of bias and a little bit of variance, but it's minimized. Yeah, so that is just this is just the same cell. So now let's do it with the test data set, and hopefully our test data set It originally was 25 for the mean squared error. Hopefully it is smaller and is closer in this like 12 range. Test mean squared error, so I want X test, scaled poly. I want my Y test. I want Y test. Then I want X test. Scaled poly. And nice. So the mean squared error is it's 16 now. So much closer. So compare the performance of the model and the test data with the Lasso set any coefficients to 0. I think, yeah. And yeah, so it set a bunch of coefficients to 0. So all these coefficients that are 0, essentially they actually have no impact to our model. So our model decided which are the important features. So a little just summary: interaction and polynomial terms can be added to linear models to account for nonlinear relationships between the features and target. We can use polynomial features to create interaction terms and polynomial terms. Error data to bias may occur when we use too many features in our model, or we don't have enough data, or too few features. Errors due to variance occur when the model is too complex. So we went from 13 features to 104, way too complex. So using Lasso regression, regularized that model and reduced the complexity, added a little extra bias. Always scale your features before regularization. We can apply Lasso regression with this. So I think I have enough time to go through this. So yeah. Let me try and go through this. And I will post this notebook, push it to a GitHub repo, so that and I'll include it in the comments of the YouTube video. And I'll include the CSV too. So let's drop the first column. It's meaningless. I always like to double check. So it has been dropped. So we fit a baseline linear regression model to the data. So first going to break it into a training test and fit the model. And then let's see how we did. So get a R squared of 0.89 for train and 0.91 for or 0.92 for the test. Not unusual to see it a little bit above. If it was extremely above, that would be kind of concerning, that maybe my test data set is not representative of the sample if it's super. So we have a function here. This is going to calculate adjusted R squared. Do you remember stats models will print out adjusted R squared, but scikit-learn does not. So 0.89 and 0.91, so not too shabby. And the training data had a mean squared error of 3, and the test data had a mean squared error of about 2. So one way we can attempt to improve this model is to include interaction terms, maybe spending the advertising budget on one media like medium, like newspaper increases the effectiveness of TV advertising in marketing. They call this synergy effects. We call this interactions. Let's add interaction terms to our data and fit a linear regression model. So we're just going to add a single one. It's a little bit easier to kind of visualize if you don't do every single one. So now we have this new term, TV times newspaper. Oh man, I have enough to do a bunch of coding. Okay. Split the data into training and testing sets. So X train, X test, Y train, Y test, train test split. And I want to do df drop sales. That's my target variable. And then Y is df sales. And then do, say, random state equals 1. So create a linear regression model. Regression, and then fit my model, lr2.fit, x train, y train. Compute the train model performance on the training and testing data set. So the first we want is r squared. So that would be lr2.score. That is going to be x train, y train. And then we want lr2, not lrs. lr2.score x test and y test. So adjusted r squared. I just want to steal this code. That will work. And I can change it for test. And you're going to need to change the model to LR2. Mean squared error, and that takes in y train and LR2.predict x train. And do the same thing with the test data set. Y test LR2.predict x test. And what did we do wrong? Oh, I needed a comma there. Score. Just kind of going down the list. So my training data set had a mean squared error, or not mean squared error, r squared of 0.9 and 0.92. Adjusted r squared is 0.89, 0.91 again. And training mean squared error is 2.8, and my testing data mean squared error is 1.9. Let me just double check that I don't get the exact same value. 1.97 and 1.9. Okay, so that's cool. So did the model performance change? So the adjusted r squared for, it's hard to say. It didn't change a whole lot. So training set adjusted r squared was 0.89 and test was 0.91, 0.89. So if that's changed, yeah, they're about the same. Where'd it go again? 0.9. Yeah, it improved a little bit by adding it, but not a whole lot. Let's take a look at the original data using SNS.pairplot. So here's TV versus radio, TV versus newspaper. Not a strong, it doesn't look like a strong relationship. TV versus sales. So what if we wanted to know about other possible interactions between the features and their effect on sales? Also, from our pair plot above, we can see the relationship between the features and the target is not exactly linear. We can use scikit-learn's pre-processing polynomial features to generate polynomial and interaction features. Let's see what fitting a model with all these features does for our model performance. So to create polynomial interaction features, run the cells below. We are only interested in creating terms with degree 2. This means we care about creating features like the square of the TV advertising budget, or interaction terms like budget times newspaper budget. So yeah, we end up with this, and this is actually pretty easy to read. Sometimes these are difficult to read because, like in that last example, we ended up with 104 features. So this one we have TV squared, then TV times TV times newspaper, radio squared, radio times newspaper, and then newspaper squared. The radio times newspaper, yeah, that covers everything. TV and radio, TV, newspaper, and then TV and radio is already covered. Radio and newspaper, yes, everything's covered. So we're going to be doing the exact same thing we did earlier. Split the data into training and testing. X train, X test, Y train, Y test equals train test split X poly, and then DF sales random state equals 1. I'm going to call this LR3. So fit it on my training data. So start with R squared, LR3 dot score. And I want to do that on X train and Y train. And LR3 dot score, and then do some of my test data set, X test and Y test. So my R squared greatly increased. Hopefully my variance didn't increase as well. Adjusted R squared. I don't remember how to call this, so I'm going to steal this code from above. Adjusted R squared. R3. X test. And Y test. And so my training, my test data set stayed pretty similar to this. So now let's take a look at mean squared error. And I want Y train, and then I want LR3 dot predict, and X train. I'm just going to copy this. Y test, and then X test. So nice. My so our mean squared error for my test data set 0.24 and 0.41. Let's compare it to what it was. Oh yeah, greatly decreased it. So yeah, that looks like that was a pretty good call. So now, one last thing, I'm going to leave this for you to do. Repeat the Boston housing data, this time using ridge regression instead of lasso regression, and see what kind of results you get. Again, I'm going to post this notebook on the recording, so feel free to kind of walk through it. And yeah, have a great rest of the day. Thank you.